Huge thanks to Marcin and Gordana for putting us together here. I really applaud your efforts, guys. Thanks a lot for organizing all this. It's a pleasure being here and actually talking abstract things for once. I really enjoy it. So I'm going to tell you about, you see from the title, it's a bit wordy, okay? But I'm going to tell you about Memristor networks, and I'm going to talk a lot about computing capacity. How much can we actually compute from a given system? And then to give this a structure, we actually focus the problem on a very specific classification issue, and that is namely deciding whether a given protein sequence is toxic or not. This apparently is a big issue in bioinformatics. So what is fascinating with this work is actually it was done by a master student, believe it or not. So Ignacio is extremely gifted young man, and now he's actually at the University of Essex doing his PhD. Okay, and actually it is very unusual for a master thesis, right? That there is a paper attached to it. So Ignacio actually produced a full-fledged paper, and it's actually has been accepted in International Journal of Unconventional Computing. I wonder about one thing. Can you see my mouse, people? If I hover, probably not. Let me see.
No.
Do you see it now?
No, yes.
Now you see it, yes?
Yes.
Okay,
but move it slowly.
Yeah, sure. I was just testing. Okay. So let me tell you a little bit about the outlook, what I'm going to tell you. So first background, the three fundamental questions that I find extremely interesting, and then physical reservoir computing as the answer to these three fundamental questions, or at least a language to talk about them. And then Memristor networks as a practical, sandbox to actually study all these ideas, and then protein classification to test the ideas, and then I'm going to conclude the talk with some summary. Okay, so here are the three fundamental questions that I find personally extremely interesting. They're very abstract. Okay, for people who are philosophically inclined, they find these questions exciting as they are. I don't have to motivate anything, right? For practical people, I tell them, well, this is about low power computation. So if we can answer these three questions, right? So the first one is, given a physical system, what sort of computation can it do? And this is known as implementation problem in cognitive science. And then the second one is, what controls computing capacity of a dynamical system? Are there features we can actually leverage to ensure we can engineer intelligence computing substrates? Is there such a thing as accidental computation? Do all things around us have ability to compute? How can we identify it? How can we harvest it? Okay, I think these are beautiful philosophical questions, and there is no need to motivate them, right? Because if we want to understand what intelligence is, what cognition is, I think this is one part of the corner that we have to visit and actually study. But as I said, for practical purposes, of course, if we understand this, then actually we know ways we can design strategies for designing low power computing systems. So this is the practical relevance of these three questions. Okay, and now, of course, Susan, she told you rather in detail about reservoir computing, and I'm not going to repeat what Susan said. I think we even share. You see, we even share the same pictures here. But I find reservoir computing a rather useful language to address these philosophical or practical questions that I showed you before, okay? So just very briefly, the idea is very simple, okay? To reiterate, rather as a memory marker. So historically, people have realized that the tedious work of training neural networks can be avoided. Okay. I'm trying to find my pointer, but I don't see it. Laser pointer. Oh, now you see it. You see. Okay, so neural network, we can avoid training it, right, by simply training the outmost layer. And that idea that occurred was, why not substitute this with something else? Okay, that has the same features that actually empower that sort of computation. And so we want to substitute this thing with a physical system. Okay, so if you're interested more in a layman sort of explanation of the whole thing. If you are new to the field, then I recommend you this book chapter I've written. So actually, it's also mathematical in the background. So it's meant as a bridge between, you know, person who is not really into mathematics of this, but who wants to know about reservoir computing. Okay. So I actually relate mathematical concepts with the practical side of it, especially if you're from different background than mathematics. And you want to understand it. But this, I think, is a good start. I highly recommend it. A lot of thought went into it. Sorry, can't resist a little bit of PR. Okay, next slide, right? So here's the thing, right? So here's the thing. This is what I have personally invested, my group. So we have invested a lot of energy in building intelligent and low power sensing substrates, okay? And it turned out that reservoir computing was a really good platform to start developing ideas. And once we were finished, the product is actually the suite algorithm. Okay, and it's I try to talk about it as a language for describing intelligent and low power sensing substrates. So the idea is extremely simple, right? If you look that part, here's the input, goes through the reservoir, you generate the output. This is the standard reservoir computing, okay? The suite algorithm is characterized by this extra feature. There is auxiliary input signal that sort of lends intelligence to the system. So if there is a favorable constellation of a problem you want to solve, of dynamical features of the system that maybe, you know, just by whispering a little to the system, you can increase its intelligence tremendously. And, you know, we were not even sure this is going to work, but it turned out to be great success, okay? This auxiliary little drive, okay, it makes a huge difference. It makes the system extremely powerful. And we tried to show that the principle works by using Memristor networks as a computing, as a physical reservoirs. Okay, so here's the picture. Here's the mental picture. You take the Memristor network and then you just put it in as a physical reservoir. So what is the input of a Memristor network? Memristor network is simply a network of a Memristor. It's an electronic element. Essentially, think of it as a resistor. Okay, just to begin with, which means you can apply electrical voltage to it, and then you can measure current through the system. What characterizes Memristor is that the state of a resistance changes as the current passes through. Okay, this is why it's called Memristor. It sort of it has a memory of the current that passed through it. Okay, so current resistance depends on a path that it experienced. And then basically by monitoring these memristances, you have another sort of information about the input, right? So basically you convert one form of input to another form of information. That is state of memristances, and that here is your vector state. Okay, here is your state represented as a vector. So it's a list of resistances, and then you can use your normal machine learning techniques, right? You can weight this to produce some sort of quantifiable output. Okay. Why memristors? Because they are low power, okay? So they're extremely useful from that point of view. And here's the simple memristor model I would just like to show you. Basically, it tells you that if you have a memristor element, you apply voltages at the ends, okay? Resistance is going to change according to that law, okay? You see that the derivative of resistance actually is a function of applied voltage and some other parameters that define the model, but essentially it has this shape, okay? This is what characterizes, and I think this is enough to know about that. There is no need to go into details. So we have implemented the SPICE model of these things, so we can actually study networks. So we have studied, you know, a large number of networks, and these are some examples that we looked at, and we applied them to a range of problems. Okay, once we were done with this suite setup, so developing this algorithm. So once we were happy with that, we actually realized, well, it can actually also be applied in a standard setting. So this input doesn't need to be something that you are sensing, but actually it can be input that you know and you want to process, okay? And that turned out to be even greater success, okay? Because this young man, my former student, Vasilis, extremely gifted. Now he's at the Max Planck Institute. So it was his initiative that we actually go to this conference on Memristor models for early detection, right? So it was computing in cardiology conference, and it was announced as a competition, right? So we were competing with the best people in the field, people who were actually using deep neural networks, okay? end goal was to take the patient data and basically classify whether you have a sepsis or not, okay? And we did, I tell you, we did not come out much worse, okay? And we were using actually these simple systems, and you compare that to deep learning that has enormous amount of gigantic space of parameters that you can actually use and optimize. We were not much worse, and this is remarkable, okay? And then also another great success was when we tried Ecg Signal Classification. And there was, for both of these problems, you know, we were actually comparing with the deep learning methods. And here, for the Ecg Signal Classification, what is really crazy, we used only one Memristor, okay? And the accuracy of prediction was amazing. Basically, you try to decide, you have the signal that comes in, and you try to decide whether the person has a problem with the heart or not, okay? And just with one Memristor, we could compete with the deep neural network people. That was amazing. And then, you know, you remember I told you here before that if there is a synergy between the system dynamics and the input you're trying to analyze, and then maybe you can really exploit this synergy by finding this drive. It is exactly what happens for these problems. So there we were actually extremely lucky, okay? And now, switching to the present talk, okay? So I was always curious, if you look at these networks, they are rather small, right? So I was always curious, okay, how would actually these ideas work if you try to really, you know, follow the spirit of reservoir computing and make the system really complex and large, okay? But the problem was that it is extremely hard to simulate behavior of a very, very large Memristor networks because there are many equations to solve. So numerics gets really pesky, okay? And then came Ignacio, yes, and then we discussed what he could do, and he had interest in complex systems, in network theory. And then, okay, I said, look, why don't we look into cellular automata model of a Memristor network? Okay. And then his interest was also in biology. So, okay, why don't we look at the protein sequence classification? And so we decided to work with this setup, basically where we actually have a Memristor network, but we just represent it as a cellular automata model. Sure enough, you do your research in literature, and there goes a paper, right? There's a paper by Adamatsky and Chua on how you can actually realize what is a good cellular automata model for Memristor network. So we took that model, right? We modified it a little. We created our own version and implemented it. And this is what Ignacio continued to simulate quite intensively. So basically, you have a network, right, that has a voltage node. It has a three values, right? High voltage 1, low voltage or neutral, and low voltage. Okay, and the Memristor only has 2 states: high resistance state and low resistance state, and that's it. So it's like a binary system. Okay, and that enabled us to simulate huge networks. So we actually explored as a network model. So we thought, okay, we should actually use models that actually people can relate to. There is a whole community of mathematicians looking into these, and physicists, you know, all complex science people, they're looking at these 3 characteristic types of a network model. So we said, okay, we actually take these and we see what comes out. So we started Erdos-Renyi. Essentially, this is a random network, okay? You just have nodes, you connect them at random, and that's it. Then we look at the Barabashi-Albert. It's a hub-like structure. It's like internet, and then what's Strogatz? It's like nearest neighbor, but you have a random long-range connections. Okay, so we looked at these, and then we realized there are some limitations. Okay, because one cannot use you cannot use reservoir computing in its raw form. So reservoir computing basically tells you just check the latest state of your system, and this is what you try to process to actually draw some conclusion about your input. But that turned out to be impractical. So earlier in 2020, we actually coined this idea of a barcode. When you actually go back in time, you do reservoir computing, but you do not look at the latest state of your system, but you actually follow the history for a little bit longer. So you could say that the state of a system, if you have a time dependence in your system, it's like a barcode. Okay, it represents what happened, what input signal it experienced. It's really like a barcode, and this was a great success. So this is actually a biological application to extremely relevant diagnostic problem of a brain disease. Okay, so back to the problem of protein classification. So we realized that these are the pictures, okay, that one has to focus on. And now, to be pedagogical, from everything I've said, I know it has been intense, okay. If you wish, you can forget it, but I'd like you to remember these two pictures, okay. So basically, they show you a typical trajectory of a system. So here we have a time. So here you have a memristors, okay? So they are either in high or low state, and that is represented by yellow or blue color, okay? And here is a non-driven system. You see that, well, it's basically, it's seismically dead, right? Nothing happens. The state is always the same. It begins here, so there is some dynamics. You see that it changes, memristors change, but then it goes down, and stays, every memristor stays the same, okay? And this is what you expect from inert system when you don't drive it, okay? And here, what we do, we actually we encode the protein sequence into voltage signals by simple translation table, okay? And then we apply to the system, and this is what you get. So you see that basically now the input sequence information gets converted into a picture like this. And that is what you can analyze to actually classify whether the protein is toxic or not. So this is idea is extremely simple. So basically what you do, you evaluate the performance of a network, and this is done in a standard machine learning way. You train your system, you optimize your parameters, and then you test it, right, on the new set of data, and then you see how well it performs. And basically the percentage of a correct classification is something that we refer to as the AP score, okay? And the findings are actually spectacular, okay? Because when Ignacio started simulating these networks, so I thought that a graph like this would be completely random and nonsense and nothing will come out. But look at this thing, it is spectacular. Because these are actually different, these are networks from the ER ensemble. So they are generated by the same algorithm. The only thing that changes in the number of nodes and the network density, okay? So you see what happens is that there are regions where the accuracy of prediction is really good. So in this region, you have a very good accuracy of prediction, and then it worsens here or here. So if you move that way, right? So for low density, it doesn't work that well. And then in the middle, it works well. And if you go to high density, it doesn't work very well. And that actually reflects on the idea of reservoir computing, that the system should be at the edge of chaos, right? Here, it's too poor, it's boring, nothing happens. Here, it's chaotic, but here in the middle, it works really well. Okay. Now, the another interesting thing is that as you increase the number of elements in your network, that the prediction gets actually worse, right? So there is what you want, contrary to the RC idea, what you might expect intuitively, right? You do not want a large system. You actually want a system that has a sort of a golden number of there is like a sweet spot in this direction where you want the right number of the nodes, yes, in your network. This was a big surprise. And same holds for Barabashi-Albert model, same behavior for Watson's progress. Now what we did, okay, we actually focused on this good region. And then we try to see, okay, let us keep the same network density and number of nodes, but let us just vary networks. Okay, let us try several networks and see, and then let us try different protein sequences. Okay, and then we made a histogram for one such a point, and this is amazing. What you see here is that distribution actually looks very regular. You observe systematic shifts in behavior depending what you do with the system. Now I don't have time to go through the details, so I will just jump directly to the conclusion. Okay, I believe I have half a minute. That should be more than enough. So the importance of what we have done, if you come from the RC side, reservoir computing side, I would like to mention that the increase in the network size decreases actually the prediction, the intelligence of the system. So there is optimal network size that is the best. And this is surprising, this is not what we are used to. The classical dogma of reservoir computing that the system should operate at the edge of chaos, it has been confirmed, okay? We have actually, we found this. What is interesting that out of the free network models in the system, Erdos-Renyi performs marginally better, but it's all noisy and it's hard to be certain. So I was not even sure whether I should put it in, but I feel as a scientist, I feel responsible for saying what I suspect might be. Okay. So what is interesting that as a rule of thumb, a raw reservoir computing, okay, just when you apply the way it's supposed to be used, it gives the accuracy prediction around 75%. Okay, to go beyond 75%, well, we have to tweak the system, and I'll tell you here below how. So in brief, RC is fine. This is my feeling, and it has been for a very long time. Okay, reservoir computing as a paradigm is fine, but I believe we seriously have to start rethinking how about the key ideas that actually empower the whole concept. Okay. For example, this idea that you just focus on the last state of the system, I don't think this is right. This idea that the system has to be extremely big, I don't feel it is right. The idea is, for example, of reservoir computing, you should not touch the system. You should just train the readout layer. You know, if you can actually deviate from it, you can get a great improvement. Okay, if you are allowed to modify a system a bit, and I think Susan also mentioned a little bit about that. Now, cognition perspective. If you are sitting in the audience and coming from that field, I would say changing in hardware does help, right? With relevant network sizes, and then there's some relevance, I believe, to how thought originates. And what we realize, there is inverse relationship between the AP score and the fatness of the tails. And here I'm talking about this distribution, okay? And what is interesting is that we are more likely to find a very accurate network in an ensemble with a lower average AP than in an ensemble of networks that perform better on average. So how to put it in simple words, intelligence can be found where you do not expect it. Let me say it like that. So there can be really performers in a sea of others. They can be performers that are extremely well, that by chance work extremely well. And we know, you know, this is evolution. And then this is the thing, you might think that, okay, these good performance, it might be that there is a synergy between a data set and a network, okay, and it's only that network is only going to work well for this particular data set, but you know, you can't be sure, okay. And then we check this, and indeed, there are actually networks in this all sea of performers that actually perform extremely well, and they actually can generalize also. So, and that is a great finding. Okay, this I think is one of the key findings of all we have done. And of course, thank the money last. So the sepsis and ECG part was financed by the recorded project, European Union Horizon 2020, that actually I was coordinating. So thank you for your attention.